Hello everyone. In this video, we are going to talk about two topics, both related to damping. One of them is called proportional or Rayleigh damping, and the other one is called Rayleigh dissipation function. So I can say both topics are related to the name Rayleigh. So what are they? The first one, which is called proportional or Rayleigh damping, is a model where you assume that the damping matrix of the system or the damping in the system is proportional to the mass matrix of the system and the stiffness matrix of the system. So C can be written as alpha times M plus beta times K, where these alpha and beta are called Rayleigh damping coefficients. Okay, and these are like numbers that you can experimentally determine. So why this model? Okay, what's the application of it, what's the limitations of that, and so on. First, where would you see this? Where is the application of this? Many places when you want to model structural damping, like you want to model the damping in buildings, bridges, structural members, and so on, you'll see that one of the models that are available for structural damping, and you can see it in many different places. You can see most of the places that you're doing finite element analysis, like in ANSYS, in SolidWorks, and so on. I can show you even in SolidWorks right now that one of the models that you can provide is called the structural damping, and that is actually a proportional damping model, and it is asking you for alpha and beta. Okay, so you can use that there, and also in control and vibration suppression models. Again, that is one of the places. So actually, let me go ahead and show you a couple of places where you see that in different software, and then we are going to talk about the origin of that. Where does this one come from? And does it have a principle behind it or not, or is it more of a practical? And then what's the advantage of this model? Why would you pick this model? Okay, so this is one of the places that you can see. This is SolidWorks. This is an I-beam, and I started a linear dynamics study. So when you go to studies, look, one of your studies is linear dynamics. So you can see the effect of different types of forces on the system. And when you go there, one of the items you have in the FEA is this guy here called damping. And if you right click and say edit, now you can say either compute it from the material damping, it's a modal damping, or look here, it says Rayleigh damping. And when you click there, there we go. Now you can provide the alpha and the beta. So C, as you can see, is alpha times M plus beta times K, and this is where you can do Rayleigh damping. And another place you can see it is, for instance, if you go to MATLAB, look. So here, when in MATLAB you want to do finite element modeling, there is this command that is now going to be replaced by a new command, but there is this command called structural damping, and then you see structural model, and then it is asking for alpha and beta. So there are a couple of places that you can see this proportional damping used for structural modeling and structural members. And this model is, of course, as I said, was proposed first time by this scientist Rayleigh, or Lord Rayleigh, basically. So is this based on physical principles and observations? Not necessarily. This is mostly a practical thing and an approximation. Why? Because the best thing about this is it allows us to still decouple the modes of vibration in a system and do the same thing that we did in systems with no damping. Remember, if you watched my recent video on modal analysis, right? Let me show you the video I just recently published on modal analysis. You saw that here I use this orthogonality of mode shapes with respect to M and K, and by using the modal matrix and pre and post multiplying it by the M and K matrix, I could convert them into diagonal matrix, and these coupled ODEs that I had for instance, a system like this, because these springs couples these degrees of freedom together. Now, by doing a simple transformation like this, x equals phi times q, where phi is the modal matrix and q's are the modal coordinates, I can go from the x coordinates to the q coordinates, where for the q coordinates, the equations are decoupled. So you can easily do that, okay? And you can find the solution for any initial condition. Now, the problem comes in when there is damping, and like a viscous damping like this. So if you have a system like this, whether the F on the right-hand side is 0 or not, let's say 0 just for simplicity, right? So it's free vibration. Now, if I ask you, could you still decouple these basically degrees of freedom from each other and come up with the modal analysis like last time? The answer is no, because this term also exists and this guy does not allow. But if I say, well, this C is proportional to both M and K, then the C will decompose a portion of it into being added to M, a portion of it to K, and you're going to be down to a system where you mostly again have M and K, and this C is will be absorbed in those two terms. So yes, you still can do it. Now let me show you how this is done. So the most important thing that this one does, it allows us to decouple the modes and do modal analysis. Let me show you how. So if the modal matrix still show it by phi, remember that k times phi equals m times phi times lambda, where phi is the modal matrix and the lambda is the matrix of eigenvalues, or the squares of the natural frequencies, okay? So this is direct definition if the system does not have this C. Good? And we use this transformation as I just showed you, and we go to modal coordinates. Now, when that C does exist, what can we do? Well, we still use the same transformation as last time. We still use that transformation, x equal phi times q. And what do we do? Again, this f could be 0 or non-zero. For simplicity, let me just set it to 0. So now, by setting x equal phi times q, my original equation will turn out to this. So it becomes m phi q double dot plus c phi q dot plus k phi q equals 0. And then I pre-multiply both sides of it by phi transpose. So I multiply both sides of it by phi transpose. From the left, you get this. Good. Now, we know this one is going to be a diagonal matrix. This guy is going to be a diagonal matrix. The only thing is, what about this one in the middle? And if I use a mass normalization, that again I explained in my previous video on modal analysis, then I can turn my phi transpose m phi into identity matrix and phi transpose k phi into the diagonal matrix of eigenvalues, or the, as I said, natural frequency squares. So the only thing is, this guy here, this matrix, what happens to that? If I call it Cm, is this matrix also diagonal or not? If it is, then guess what? I have decoupled my equations, because every coefficient matrix is now going to be diagonal. The I here is diagonal, that lambda is diagonal. If this one is diagonal, I'm done. But is that going to be the case? Well, if C is proportional to M and K, yes, it is. Because now, look, all I need is to replace it by alpha m plus beta k, and it is going to be alpha times I plus beta times lambda, just like that. Extremely easy. Okay? So now this C is going to be alpha I plus beta times lambda, and that will be times q dot. Therefore, your equation becomes q double dot plus alpha times q dot plus beta times lambda times q dot plus lambda times q equals 0. And guess what? Here, this is, or if you want to combine alpha plus beta lambda, that is a diagonal matrix, this I, as I said, is diagonal, lambda is diagonal. So now all of your equations are going to be decoupled, and that is the biggest thing. Now, if you write an individual equation, your individual equation will be like this. Okay, remember, when you have viscous damping, your individual equations should look like this, or if it's homogeneous, it's like that. Then, comparing these with each other, you can see the definition of the damping ratio zeta. What is zeta? Well, here you can see that the coefficients of Q dot in here is 2 zeta I omega ni, correct? And then in here, what's the coefficient? In here, the coefficient is alpha plus beta times lambda, and lambda is omega I squared. Lambda I is omega I squared. There we go. So now all I need is to divide both sides by 2 omega ni. And that is my damping ratio, which is this formula. Okay, so now you can see that, there we go. Now I have decoupled ODEs for each one of the modal coordinates, and I can find the omega I is still there, and the damping ratio is related to the alpha and beta, those Rayleigh coefficients. And not only that, there is another important thing here, that your damping coefficient is not constant here. It is related to the natural frequency. When there is no damping, remember this C, this zeta for a mass spring damper system, it was C over 2 square root Km. Now, is that related to omega n? Yes, it is. Here it's a little bit more complicated, because here, if you want also, this, you can write it as C over 2 times square root K over M times M, correct? And this is basically C over 2M divided by 1 over omega n, correct? So in there also, zeta was a function of omega n, but here it's more complicated. It's a function of omega 1 over omega n and the omega n itself. So the relation here is more complicated, and it depends on this alpha and beta. So you can say that my damping could be frequency dependent. So for different frequencies, with tuning alpha and beta, you can have different basically damping ratios. Okay, so this is why this model is picked. It's all based on practicality and decoupling. Now, with what I said, are there limitations? Of course there are. What is it? First of all, as I said, this is an approximation, and it's not really based on rigorous physical principles. So for some systems, it should not be accurate. Well, where? This is when damping is due to friction, not due to basically viscous fluid, when there is material hysteresis, and when there are nonlinear effects. And when the system shows some non-proportional damping, systems that have a localized damping, like damper only at one point of it, not all over that structural member or something, this can not be a good representation. So although it's very popular and it's used in many different finite element analysis software, it has some limitations. Okay, so this is structural damping using Rayleigh or proportional damping. The second thing that I wanted to just briefly mention it to you is called the Rayleigh dissipation function. What is this? This is a scalar function that when you are using Euler-Lagrange equation to get the equations of motion of the system, this is used to show that non-conservative force of the right-hand side. Remember, if you watch my videos where I used the Euler-Lagrange equation, the way that I wrote the Euler-Lagrange equation is, and I can replace this with L if you want. The way that I did it is, I said d over dl of partial of L with respect to Q dot minus partial of L with respect to Q was a generalized force that was non-conservative. So this is how I always wrote the Euler-Lagrange equation, okay? Now, another way to write it is like this. Okay, so you can show that right-hand side as, basically, if you take this term to this side, you can write it as negative partial derivative of some function with respect to the q dot. Okay, so that non-conservative force can also be written as negative partial derivative of a function with respect to q dot. And for viscous damping, it is very easy to show that when the damping is viscous linear and isotropic, you can show that that function is simply 1/2 cx dot squared, or 1/2 cq dot squared in general. Okay, so that's all it is, because if that's the case, then partial of f with respect to x dot is clearly, in this case, is cx dot. And if you take it to the other side, it's going to be negative cx dot. And that is what we always used when we had a mass spring damper system. That non-conservative force on the right-hand side was negative cx dot. So that's just another way to show it. One last thing I want to mention about this is this guy here, this function, is not actually an energy function. It's not like the kinetic energy and the potential energy that you have in the Lagrangian. It's not an energy. It's mostly a power, a dissipation power. Why? Because the work done by a damper is negative of the integral of the force times displacement with the negative. That negative is because the damper is against the displacement, so that is a cosine of 180 degrees, the angle between them, because this is like f times dr, and f of damper has this magnitude, dr has magnitude dx, and the angle between them is 180, so cosine of that is -1. Now f of damper is cx dot, linear isotropic damper, and then dx, you write it. Now here I divide this dx by dt, multiply by dt, so this term becomes, this is going to be another x dot, so it becomes cx dot squared dt. Now I take a time derivative from both sides of this. The time derivative of work is going to be the power of damper dissipating energy, and then the derivative of integral of something with respect to t, derivative and integral of, they are opposite functions of each other, so they can cancel each other, so you get cx dot squared. So you see, this cx dot squared is basically the dissipation power of the damper. You just multiply it by 1/2. So when you take that partial, that 2 and this 2 would cancel, and you get cx dot, not 1/2 cx dot. So if you ever hear the Rayleigh dissipation function and you see that it is used in the Euler-Lagrange equation, I just want you to know what it is. And also, if you heard the structural damping by proportional model, or Rayleigh damping and Rayleigh coefficients, damping coefficients, what is it, where it comes from, what are the advantages, disadvantages, and applications. So hopefully this video was useful to you. I'll see you in the next lecture. Thank you.